All right. Oh, I need to turn this on.
Does it work? You hear me? Yes, I think it works. Okay. I'll wrap it up with a bunch more problems. There's many more where those came from, but okay. Here's going to be very. Let's warm up. It's day 4. Here's a very short one that I came across by accident, and the question is just: is this just a freak accident, or are there more like it? That's the question. So here's a very, very basic statement. If you've got a nice function, 2 pi periodic, and you have a bound on the L infinity norm. So suppose the L infinity norm is 1, so you're trapped between +1 and -1. Now there's a very simple picture. The picture is if the graph of the function is long, right? I mean, if the length is big, right? If you go up and down a lot, you're going to have critical points. Because you're sort of trapped in a box. Imagine putting a snake in a box, right? And then the snake has to bend. And every time the snake bends, you get a critical point. So this is not very complicated to see. And what happened a couple of years ago is I was working on a completely unrelated problem involving optimal transport. And what happened is there was an inequality that popped out. That inequality that popped out was A is less than B is less than C. No, they tend to look like this, right? And I realized when you erase this, which is true, you remember this is inequalities. You get this, okay? So this was sort of a byproduct that has no optimal transport in it. It's completely just a statement about functions and derivatives. It's not very hard to prove. The thing I was interested in was B, but then I saw this. I'm like, that's kind of funny. And again, you can plug in sine kx, and you realize it's sharp is sort of along an infinite family. So sine kx scales exactly right. You get k, 1, and then you get k squared over k, which is k. Yes?
What's the constant?
I never computed the constant.
The other inequality, you get like either 2 or 4, right?
Yeah, exactly. No, I think you can compute it. It's probably not. It's probably like piecewise linear. Although I never proved that. There was some abstract nonsense proof with a constant. But it probably is order 1. I mean, it's not 1 over 10 trillion. It's a nice constant.
I mean, but the first one is like this.
The first one is very easy. The first one is sort of to inspire, because now there's 2 inequalities, right? So can you interpolate this? Are there more like it? Is this just a freak accident? I don't know. Here we go. Very short, very simple problem. Okay. Next one. So this one, this was very funny. The pictures are weird. It came out of PDE problem, but you can ignore the phenomenon that has nothing to do with PDEs. It's a statement about orthogonal functions or certain types of orthogonal functions, and the most basic statement is the one you learn in linear algebra, right? If you have an eigenvector, then minus v is also an eigenvector, right? Because it's really an eigenspace. But from a Fourier analysis perspective, when you expand a function with respect to an orthogonal basis, if you replace phi k by minus phi k, nothing changes, right? Because the minus cancels in the expansion. So if 200 years ago Fourier had been in a different mood, maybe we would use minus sine x and minus sine 2x and minus sine 3x, right? Nothing would change. Okay, so this is very uncontroversial. But what you could now do is you could do the following. You could think of phi k as eigenfunctions of the Laplacian, but you could also think about just sines and cosines. I'm going to start with sines and cosines. So what you could do is you could fix a point in your domain, and then look at this following funny sum. And what the sum does, it takes the function at the point, and it's flipping the sign so that it's positive. And then you sum those up. There's an entire paper that you can read that explains why this is interesting, but I'm just going to show you pictures why this is interesting, and the motivation maybe doesn't matter. So here's an example. These are sines. Yeah, again, not very controversial. It's a 4th day of a conference, kind of chill. Sine 2x. Now what we can do is I'm going to pick the point x is 2, so take each individual sign and I flip its sign with a g, right, in front, so that it's positive in 2, and I'm summing it up, and of course what you see is a big peak in 2, right? Big spike, because they're all positive. I mean, that's how I designed them to be. So how about I add more terms? Okay, how about I add some more terms? And you start getting something pretty funky, right? You get these peaks coming out of nowhere. Now, it's not super hard to prove in this case because it's science. We know everything about science. It's nice. It's friendly. Although I didn't actually prove anything about it in the paper. I'm not sure anyone wrote this down, but here's the picture, and you can kind of see what's happening. And the thing that's really funny is this seems to be a much more general phenomenon. Okay, 1,000 terms, right? So it stabilizes. There's a limit. There's certain resonances at a distance that show up. So I think we had this 2 lectures ago. Signs care what they do far away. They're not random decoupled objects. They kind of care what's going on. Funny. Now, what's funny about this is you can do this at a much greater level of generality. So this is the best I can do numerically that's somewhat non-generic. So what I'm going to do is I'm going to take a quarter disk, okay? I'm going to take a quarter disk. So this is still kind of a nice object. I'm going to impose 0 boundary conditions, right, Dirichlet, and I'm going to look at eigenfunctions of the Laplace. So these are the sort of natural analogs of sine and cosines. And I'm going to sum them up in a specific point. I'm going to show you the same function. And what you see here is, I mean, so I did like 600 because I'm not good at numerics and at, it's Bessel functions and okay. But what you start seeing here is you've got the big peak. That's the point I picked. That's where the sines are all organized to sit on top of each other. But then there's a little peak in the back that pops out. It's weird, right? And then I said, okay, what are the other natural boundary conditions? Neumann. So here's the Neumann picture. So normal derivatives are 0, and it just changes the index in the Bessel function. So what do you see for Neumann is this. And you see there's kind of a funky little peak here, but there's an entire ring that starts to form. And I would assume that if you sit down and you start opening, Watson, the book on Bessel functions, right? And you're really motivated, maybe this can be proven, maybe. But the thing I want to point out is I picked a quarter disk kind of at random because I looked online, what domain is not the disk, and you can find nice formulas for the eigenfunctions, and they were like, oh, quarter disk, it's some undergrad exercise for separation of variables. I'm like, okay, I'm going to take that, right? So it seems to be an interesting phenomenon that seems to hold for structured domains, but not necessarily too structured. So what I mean by this is okay, if, maybe on S1, on the torus, you believe me, right? It's not too surprising. Here, I think it's kind of interesting. I'm sure that if you were to put a little dent into the domain here, you deform it a little, and you rerun it again, it's all going to break down. It's maybe, so coming from the PD perspective, my guess is it's something like, integrability of the geodesic flow. But I don't know. So there's a very interesting phenomenon involving certain types of natural orthogonal functions that generalize sines and cosines.
So again, so you are summing just...
Yeah, so I get these guys, right? I mean, it's a sequence of functions, phi 1, phi 2, phi 3, and I picked this one point here that, I don't know, you can probably see it's like 1 over square root 2, 1 over square root 2, I think, or...
This is the point you pick it for the sine channel.
That's right. So what I'm doing is, you see this bright yellow spot, let's call it x. So the sum is simply k from 1 to n, sine of phi k of this point times phi k of y. And this is a fixed point. I mean, probably it's 1/2, right? I think. And now what you see plotted here is the function f of y. So the sines are all aligned such that in that point, of course, and this is of course going to be a very large point because I'm working this, but you see this ring showing up. No idea why. And as far as I can tell, I mean, this is not a cherry-picked example. This is the one where you Google online Laplacian eigenfunction, explicit formula, not the disk. This is the first you find. And you could do many more. Okay, questions on this?
Have you run this same simulation, moving this point around?
Yeah.
Does it always look like this?
So it depends a little bit on the domain, but yeah, kind of. It's weird, right? I said, okay, I don't have any more pictures. I mean, another one I tried, just because why not, unit square. Unit square, what happens is, if you pick the center point, you start getting like concentric circles here, which I thought was weird. If you put something that's not centered, that's kind of breaking the symmetry, you get like weird ghost hallucinations over here, stuff like this. Bounded Dirichlet, yeah. That's Dirichlet. I mean, it could also be that, if you do the computation for like 1,000,000 terms, it all disappears. I don't think so. I mean, these are like 600 terms or something, and this is like half the size of the other one or a third, and it seems to be numerically quite stable. Okay, so here's a puzzle for everyone. No idea. Cool, okay. After confusing orthonormal functions, let's do something even simpler. This problem is now 100 years old. And we know very little, and I'm going to tell you that the question is completely elementary. It's frustratingly high school. The question is the following. We're given a domain, and you can take the unit square, you can take any other domain, but the unit square is a good example. And I want to pick a set that has the following property. It's a one-dimensional set, so think of line segments. And every time a line, an infinite line, intersects the square, it also has to intersect my little subset that I chose. And the question is, how short can it be, this magic set? So here's a simple example. Turns out if you pick the boundary of the square, every line that hits the square hits the boundary of the square, and therefore it hits the set. But it turns out you can do a little bit shorter, right? You can actually do, you can do this. You can do 3. You can omit one side of the boundary because the only kind of problematic line would be this one, but by making this epsilon larger, you're fine, and so 3 is doable. Well, you can do a little bit better still. You can do this. So this is people from combinatorial optimization came up with this. These are like Steiner trees. And one nice way to think about this question is if I walk around, if I'm a two-dimensional person walking around the square, it always looks like the square is solid, right? It's one way to think about it. As you walk around the set, if you look at it, you can never see through the square. So what's the most economic fence that blocks the view? That's one way. Or what's the most interesting piece of artwork, right? You could put it and say, oh, it looks like a square, but then it turns out it's not a square, right? Actually, it's not a bad idea. So the thing people like this problem is for the following reason. This is not the optimizer. The optimizer is this one. Probably. It's not known. This is since the 90s, people think that this is the most extreme, sort of the most efficient example. People from calculus of variations like it because it's disconnected. Right? It's like a symmetry breaking kind of thing. Like, why is it disconnected? And the thing that's funny about it is there hasn't been very much progress. In fact, I'm going to tell you almost everything that's known. From a Fourier analysis perspective, okay, either I could say it's beyond, but it's not really beyond because it's like Radon transforms, right? You're talking about like kind of a Radon transform lower bound. That's one way to think about it. Also projection geometry, right? Integral geometry is also Fourier analysis. Okay, so to give you another example, that's the unit disk. And this example is meant to convince you that things are really quite complicated. So this is the conjectured example for the unit disk. And again, it's been known for what, 45 years. What's known rigorously is very, very little. Now let me tell you what's known. This is essentially what's known. So if you have a convex domain, like the square or the disk, and you have a set, so these sets are called opaque sets or barrier sets, then the length of such a barrier is at least half the boundary. So in the case of the unit square, this gives us the lower bound 2, which is very far away from the 2.6 that is believed to be the case. Moreover, this has an essentially trivial proof. In fact, how about I draw the proof? Maybe I have it on the next slide, but I can actually draw the proof. So suppose we have the square. Oops. You've got the square, and you've got a magic mystery set about which you know very, very little. Right? We don't know what it is. In fact, it doesn't even have to be contained inside the square. It can be anywhere. Now what happens is the sun, okay, for people who know the stuff, it's a Favart length argument from projection theory, but think of the sun, and the sun is here, and the sun is casting a shadow, and because every single ray of light is touching the magic set, I know that the shadow cast by the mystery set has to contain the shadow of the square. So the square has a certain shadow here, which you can see, it's here. And whatever the mystery set is, if the sun shines from here, it casts at least a shadow that contains this. Because if it didn't, right, I mean, if the mystery set didn't have this shadow, here, if this was missing, this would correspond to a line that touches the square, but it doesn't touch the mystery set. And that's forbidden. So we get this very nice sort of projection argument. And now here's a fun question for everyone. If I have a convex set and I have the sun going around, what's the average length of the shadow? This you can compute, and in fact it's a formula by Cauchy that says it's just the boundary, length of the boundary with a constant, which is kind of funny. And then you can say, okay, what's my mystery set? Well, I don't know anything about my mystery set, right? I have no idea what it is, but what I certainly can do is I can say, well, my mystery set, if it's, say, rectifiable, and there's some interesting rectifiability issues here, but if you optimize over, say, piecewise differentiable, it's probably fine. Yeah, does the extremize exist? Okay, let's not even go there. We're very far from any of this. But if I have my mystery set and locally it's a line segment, well, I know everything about the shadow cast by a single line segment. It's a sine. Right? Because if the sun is here, I get the length of the line segment times 1. If the sun is over here, the shadow being cast is 0, and that's exactly what's cosine, right? Cosine pi over 2, cosine 0. So you know exactly what's happening. The average length of a line segment of length epsilon is 2 over pi times epsilon. The average length of a shadow cast. Now what can happen is in my mystery set, of course, well, what could happen is it could be a very, very complicated mystery set that has some crazy fractal structure, right? I mean, probably not, but could be. And there could be some parts where if the sun shines here, the ray goes through the mystery set twice, but that's good for us. That makes it longer. So the worst case is if every single shadow that's being cast is cast uniquely, and in that case, you get exactly the bound. Okay, and one problem with this bound is it's optimal. It's basically optimal in one case, and that case is the following. It's an epsilon by one rectangle. So the bound here says that the length is at least half the boundary, right? That's Jones's bound. So it's at least 1 plus epsilon. But there is a very simple set that does the trick, and that's 3 sides of the boundary. Same example as before. And that has length 1 plus 2 epsilon. And now you can make epsilon very, very small, and you realize you can't improve the constant in Jones. You can't do better than a half, but it's kind of clear that the only way to get half is if you have a very eccentric set. It's not satisfying at all. So here's the picture. Okay, so actually I kind of explained this proof. This is Cauchy's mean width argument, which you can also prove with Crofton integral formula, if you know what that is, because a convex domain has the property that every line, almost every line with respect to the kinematic measure hits it twice. So not too hard to prove. This I drew, that's the proof. But it's not happening, right? I mean, there's clearly, there are clearly lines that are going to hit the set twice. Yes?
What's the kinematic measure?
Short answer, don't worry about it. Medium answer is it's the measure. It's a measure on lines that's invariant under rotation and translation. So every line is equally important, and it's the natural way to do these projection type of arguments. It sounds much more complicated than it is. It's the natural thing you would do if you had to put a measure on lines. I guess one could. People don't usually write it on the ground. They write it now too, for historical reasons maybe. You could. It's not the orientation. It's orientation and location. Yes, something like this. But people just write out usually just RD and say kinematic and. Trust me, there's no subtlety hiding here. I could explain this in high school if I had an hour, which I do, but I have many problems. So here's the best lower bound. It's It's an improvement of Jones, so the answer is somewhere between 2 and 2.6, and the best lower bound is this. And this argument essentially exploits the fact that you have to have something that has to touch both. Somehow there's something missing. So I worked very hard, and I got almost nothing, but I can show you what I got. What I got is I got a quantitative refinement of Jones, which is the following. So suppose we have a magic set that does the job, and I'm going to think it's a union of line segments, and I can wave my hands enough to convince it's a union of line segments, maybe infinitely many line segments, that's fine. What I'm going to do is I'm going to turn this into a measure on the torus. And the way I do it is each angle corresponds to an angle here. And because we're in the Grassmannian, right, the line has two directions, I'm going to split the length in half. So I've got this brown line at 45 degrees, and 45 degrees is the same as 225 degrees. So half the length is at 45 degrees, and half the length is 225 degrees. And this breaks the line symmetry. This is sort of, okay, I haven't seen this in the literature, but it's the natural thing to do in some sense. But the statement says, if you have a bounded convex domain, everything's nice, and you have one of these magic sets of length L, then you can do the following. You can build this magic set for the set in this way, and you can also build the measure corresponding to the boundary of the set itself. And you get the following inequality. So you get that these two measures are very, very close to each other when measured in Sobolev -2, which is a very rough space, right? This is not a very good bound, but of course, it's a norm at least, so this is at least 0, which tells me that this is at least 0, which is Jones's bound. But it also tells you that if Jones's bound is almost saturated, like here, right? I mean, here in this example, when epsilon gets small, the Jones bound is essentially saturated up to an arbitrarily small factor, then this theorem tells you that the magic set has to be comprised of many line segments that are oriented like this. It doesn't tell you where they are, but it tells you that there are many line segments that look like this and some that look like that. So if Jones's bound were sharp, the magic set has to essentially point in the same direction as the boundary. And I've been completely unable to use this for any quantitative improvement on the square, even the square. Even though now you know if it's close to 2, then it's basically parallel to the x and y axis. No idea. Okay, questions on this? It's some good fun. It's not as, so it's well known in certain areas, but these areas tend to be fairly far away from Fourier analysis. Computational geometry, people in CS in the 80s and 90s, there's a lot of papers. They're mostly concerned with approximation algorithms, finding examples of good sets quickly. It has, as far as I can tell, not been studied from a Fourier analysis perspective, even though it's clearly a Fourier analysis problem. And this is lines and sets, right? Okay. There's no question. Next problem. Yes?
Why h minus 2?
It's what the proof gives. I took it. I mean, if it had given me h minus 1, I would have taken that too, but it's what comes out. I'm not saying, okay, one could check whether it's sharp. I didn't check whether it's sharp. Because I didn't have any alternative proof anyway. I worked very hard. It's the only thing I got. The proof is not very hard.
Is it free analysis?
Yeah. It's honestly, you sit down, you probably get it by the end of the talk. It's very simple projection, counting. It's 3 pages.
I like your free
No. You overestimate how hard this proof is. A very simple proof. Frustratingly difficult to get more for me. But
so is it one of the problems that you believe that's complicated?
No. I think, no. There's stuff that can be done here.
You think so?
Oh, yeah.
No, I mean the general problem, the problem with the square.
No, I think this has not been studied enough.
I see.
This problem, there's stuff that can be done. This is not the Riemann hypothesis. This is not Littlewood's cosine problem. This is not Charlot's cosine problem. There's stuff that can be done here for sure. Okay. Next problem. So this is always funny. This question, okay, I would have considered this a very, very dumb question, okay? And maybe you would too. So I'm going to start with a story. Because I did not come up with this question. I was asked this question by an economist. And the question that I received was, how do you average the income someone received in the last year? And I said, well, guys, come on, like you sum it up and you divide by 12, right? You see, it's a dumb question, right? But then I was told the following, and apparently this is true in maybe Switzerland or Norway. There's certain countries where the following is true. You can declare yourself to be an artist. What does this mean? Well, if I'm an artist, right, and I write a novel, I publish the novel, I make a lot of money that year. But then I have to write the next novel, and it's going to take me 5 years where I have basically very little income. So if I get taxed on an annual basis, I pay a lot of taxes that 1 year, and I lose a lot of money, and I don't get any money in the other years. It's kind of unfair. So if I can declare myself an artist, I get taxed on the average income I received in the last 5 years. Some countries allow this, and then, okay. So, what I'm going to talk about now? Well, suppose we have a function that's, assume anything you want, compact, complex supported, C infinity, real analytic if you want, it doesn't even matter. And you want to compute the local average at a point. Then from Fourier analysis, you used to say, okay, well, there's a point and there's a scale over which I average, and that determines the quantity in question, right? Hardy-Littlewood maximal functions, Poisson averages, Gaussian averages. That's it. But the question is actually, what's the best average? Like, how do you actually average? You could average with respect to a Gaussian, you could with respect to a Poisson kernel, with respect to a characteristic function. And for 99.9% of the problems in real life, it doesn't matter. They're kind of comparable anyway. And if you prove, if you use it if you use Hardy-Littlewood maximal function to control some error, it doesn't matter if you lose a factor 2, right? Or 1.01. I mean, it doesn't matter. But I'm going to show, I'm going to have some convincing slides why this is a good question. And the thing I want to emphasize is this is a very atypical question for a math audience because it's half philosophy. The reason is you have to kind of identify what you mean by best. You have to actually think about it as what do I want an average to do? What is a desirable property for an average to have? And of course, there are probably 20 legitimate answers. Not just one. And then the second part is you have to identify, if I say I want this property, well, then it's your job to find out how to get that property, what sort of averaging functions would do this. So this is actually the only two examples I know where this is really done in math is cooperative game theory. When people have to agree on how to divide cake, there's a discussion of what axioms a fair solution has to satisfy, and there's different sets of axioms leading to different solutions. The other example is, interestingly, computer vision. So if you look into the question of how do you make a picture nicer or rougher so it doesn't take as much space in the computer, there's discussions of what properties does the downsampling have to satisfy. Okay, so here's what I want, and you're free to disagree because it's axioms. Okay, so what I want is I want translation invariance, right? I mean, if you move the function, it's the same as moving the average. I want that the average of a constant is a constant, and preferably the same constant. Very uncontroversial, right? I want linearity, because I don't think I have to argue for linearity, but feel free to disagree. So really what you kind of do is you're looking for convolution, right? You want to convolve with something, and the question is, what do you convolve with? And so here's my example. Suppose this is, I don't know, something. If I average with characteristic functions, I get this. If I average with the exponential distribution, say, I get that. Now you're going to say, well, they're kind of the same curve, right? I mean, they kind of do the same thing. There's no big problem from the moment you disregard constants, the question is meaningless. But if you get taxed on the orange or the green curve, you're suddenly going to have an opinion whether you prefer the orange or the green curve. So just multiply the scale with like 10 trillion. And suddenly it kind of matters, right? Especially if economists come to you and say, do you have any mathematical reasons why we should compute taxation like this? You kind of want to have a better answer than we've always used characteristic functions, right? You got to try. Okay, so you need one more property, and now the question is, what's the right property? I mean, think about it. What would you do? Think about it. What's actually the property you want? What is a good property? Agnostically. You don't know what the problem is going to be. What's the right thing to do? So, okay, I'm going to show you what I thought. I thought, okay, I want constants to be mapped to constants and the same constant, so that's that. I want to fix some scale. I think that makes sense. That's part of the problem. You have to tell me whether you average over a week or a month or a decade. So that's kind of problem specific. But the other property I want is I want this convolution to be as smooth as possible. Why not? I mean, not the only thing you could do, but something you can do. So what I want is if I convolve this thing, right, because it exists at a certain scale, I immediately know that the outcome is going to be like differentiable and nice. And what I want is, so there's going to be a constant here. The constant depends on the window you use to convolve. I want that constant so as small as possible. That's one way of saying it's the smoothest possible convolution. Of course, you see immediately there are many other ways to do this. Well, LP, L infinity, you could do other types of modifications. You could look at the third derivative. I mean, there's a lot of things to do. But this is the one I wrote down. And then it became so interesting, I never looked at any of the other ones. Questions on the setup? Okay, so first question is, can this constant be 0? Or probably not. Why not? And it turns out this leads to an uncertainty principle. Okay, so I just said this, you can do many things. So the uncertainty principle you get was, it's very confusing because you don't usually see new uncertainty principles. So the first thing I did is spend a month reading the literature because there's 800 uncertainty principles. As far as I can tell, it's new, but okay. So what's happening is you get two parameters, alpha and beta, and it's a usual type of thing where you take a Fourier transform and you take the spatial domain and you put sort of weights on it. The thing that's unusual about it is the spaces. It's L1 and L infinity. Usually you have more LP, P between. And the problem above corresponds to one space dimension, and you just fix, essentially, you fix a spatial scale. That's the variance of the problem you have. So if you fix the fact that the integral is 1, because that's what I want, and if I fix this to be lambda, this tells me that this constant, so this happens to be the constant in the inequality, which you see by L2 duality, it's very easy. This constant cannot be arbitrarily small. The question is, how small can it be? And which function extremizes this? Because that is the smoothest possible function in the way I described it. So it turns out you can specialize more. You can say, I fix variance, right? You get this inequality. So the question is, what can you say about the extremal function here? This is a very, very elementary classical Fourier analysis problem. And what's funny about it is when you do extremal functions in Fourier analysis, usually everything's very smooth. It's usually a Gaussian. Sometimes it's 1 over 1 plus x squared. Usually it's very, very nice. But here there's a new ingredient. And the new ingredient is I measure this in an L infinity. I don't care how big the oscillations are. I just care that they are uniform, not they don't get uniformly too big. So what can happen is I assume there's a natural conjecture which is you're going to saturate inequality, which means you're going to attain this thing infinitely many times, because if at some point you stop attaining it, there's a little bit of wiggle room where you can perturb the function a little bit more and you gain. Weight heuristic. But what this means is it means this, right? I mean, if you attain it infinitely many times, it means that the Fourier transform of the extremizer does not decay exponentially. And that means it's not a Gaussian. And it's also not 1 over 1 plus x squared, so it's something else. And how smooth, I mean, in fact, yeah, I mean, okay, so it's what's the extremizer here? So let me tell you the answer. It turns out maybe the answer is the characteristic function. Which would be fun, because then you can go back to economists and say, well, we always used to do it like this, but now there's at least one axiomatic reason in which this makes sense. It's the canonical thing to do. So the question is the characteristic function u, so just, okay, on an interval that corresponds to the scale that you prescribe, is that the extremizer for this inequality? Turns out, locally, yes. Globally, I have no idea. The local proof is actually quite easy. You can tell from the fact it's 2, 3, 4, 5, 6. If you just do the local perturbation analysis, you start having to work with certain types of special functions. And you can do it by hand. And then other people said, oh, if you know a lot about special functions, you can do all cases. So locally, it's optimal, which is kind of a funny indicator that maybe classical averaging this framework makes a lot of sense. But it's a nice Fourier uncertainty principle. There's a question about extremizing the Fourier uncertainty principle. The extremizer should be nice. So I think that, you know, if you normalize the scaling, I think that this is going to be, like, if the L infinity norm is 1, I think the extremizer, this is going to be 1 for the extremizer infinitely many times.
How much multiplied by?
By psi, yeah. So you get better derivatives in some sense, right?
This is why, okay, so if a basic function will give you a sinc function.
A sinc is 1 over x.
And then you give it
Well, it's 1 over xi, so you get 1 over xi, it works out exactly. And it touches infinitely many times. Okay, so it turns out this problem becomes, so I mean, the continuous case seems to be non-trivial. You can see a little bit more about the discrete problem. Wait, so how long do I have? 12:30? But people are hungry, right? So not exactly 12:30, more like
15 minutes.
15 minutes. Okay, so here's a question. What if you do this discretely? Discretely makes a lot of sense because when you actually compute taxation, for example, you have time series. So you have a function on the lattice. And you have a window, and the window is naturally supported now between minus n and n. The scale is an integer. You can prescribe this like this. And the question is now, what's the best G if you do everything discretely? Same question. So I think, Jose had the discrete derivative on the slide once, right? This is just the value between consecutive entries. Same story. Oh, yeah, I have it too. Okay. So it turns out you can solve this problem in some special cases. So this is the case of essentially one derivative. And it turns out no matter how so this is the object you want to minimize, over all possible functions f, the convolution with the magic function u should be as smooth as possible. And it turns out the best way to do it is you pick a constant characteristic function. So the continuous conjecture is true in the discrete setting, which is nice. Now, then you say, oh, wait a second. If I know the discrete case, I can take a limit, right, and go to continuous. And we couldn't. And we tried for a while. And there was some weird subtle issues showing up all the time we couldn't handle. So I take this as an indication that, yes, in a continuous setting, it is actually true. But I don't know how to prove it. And the second thing that was nice is the proof worked so well that we could actually handle the case of second derivatives. So you could say, oh, I want the derivatives as smooth as possible. That makes sense. But you could even say, oh, I want the second derivatives as smooth as possible. Same question. So now there's a Laplacian here. And it turns out the optimal rate is this. And the optimal function u is the triangle function. So, I mean, this is a Fourier kernel and stuff. So if you have a time series and you want smooth second derivatives, this is the window that you convolve with. Note that this is the convolution of two of these characteristic functions. So the solution for one derivative convolved with itself gives you the solution for the second derivative. Now you think, oh, wait a second, I can generalize this, right? I convolve one more time, and we couldn't do it. Everything got messed up, and it turns out you can actually remove the requirement that, so we proved it for positive definite functions, but you can drop that and the same result is true. Okay. No idea how to do higher derivatives. No idea at all. We're not even clear what the extremizer is supposed to be. I'm going to go quickly over the proof. The proof is essentially, you're on the lattice, so the Fourier dual is the torus, so you have really trig polynomials on the torus, and then essentially you need to prove inequalities of this type, and these you can prove by going through the proof of Chebyshev's theorem, and making the appropriate modification whenever necessary. And there's the second, so I mean you have to like it's a kind of a funny maximization problem because it's asymmetric, but turns out the extremal function looks like this, and you can do it all, and it's not too terrible. And that's the second inequality that you prove for polynomials. And the higher derivatives just correspond to inequalities like this that really sound like Chebyshev, but somehow everything stops working. And the extremizer here looks like this. Okay, questions? We're good? Okay, then I think I'm coming to the last problem. The last one I like a lot. It's very elementary. So suppose you're given a function on the torus, and the function is a pure frequency. Okay, it's one cosine. Then you know what the roots look like. The roots are lines, and you know the gap between the lines, and you know that each ball of appropriate radius, being sort of inverse wavelength, contains a root. You know the gaps between the roots. Now the question is, what happens if you've got sums of cosines, right? You start summing stuff up. It's a little bit like the Littlewood cosine problem. Surely you have to have a lot of roots, and there's a classical result in 1D that kind of tells you if I start summing at a certain frequency and I go to a larger frequency, which is kind of important here, then you know what the sharp rate is and you know what the extremizing functions is. And it's not a very well-known result, but 1D is kind of solved. And then there's this absolutely beautiful paper that generalizes this. So this is not, I'm giving you the 1D version. There's a version in higher dimensions as well, which looks the same. But suppose you've got a function on the torus, and it's just the sum of cosines with arbitrary coefficients. There's no control. I mean, it doesn't matter what the coefficients are. Then what happens is you can guarantee that there's a root in each interval of a certain length, and the length only depends on the frequencies that show up. Okay, so just to have a picture, it's something like, okay, if I have a sine at this frequency, I know there's a root every wavelength thing. Suppose I have a higher frequency object like this, then the inequality, or the statement here basically says, okay, if you have now a linear combination of these two, so A times this plus B times this, you have a root in every interval of length this plus this with a constant. And it works in higher dimensions just the same. So it's kind of nice. So in higher dimensions, there's a bit of a slack that you can see. What happens is, it turns out it doesn't actually matter. Like if you've got frequencies, so in higher dimensions, you have multiple directions into which a frequency could point. Now what the first result tells you is you sum all of them up, and the second result says it actually does not matter. You can just look at all the frequencies you get. It doesn't matter what the dimension of the eigenspace is, and you get the same flavor of result. And the proof of this is actually super easy. I'm going to show you the proof of this. Again, it works in higher dimensions. The proof is the following. Suppose I've got my magic function f, and I want to prove that it's got a root in every ball of a certain radius. So what you do is you convolve. So suppose my magic function is here somewhere, and I'm sitting in this point, and I want to show that there's a root nearby. Well, suppose the roots are all very far away. Then what I can do is I can convolve with a suitable function, like a sort of a compactly supported function. I could convolve my functions if the nearest root is here. Or maybe it's 2D, right? So the roots are maybe here, they're far away. So here the function is 0, here the function is positive. Now if I convolve this function with a sort of a locally comported, compactly supported function that lives at a certain scale, what's going to happen? Well, here it's all positive. The function's positive in here. If I convolve, I take an average of positive functions. It's all positive. It's going to stay positive. The thing, so suppose h is compactly supported like on this scale. The thing that's going to change is this front may move in, right? Because when I'm over here, I may take an average over this, and then the negative part here could win against the positive part here. And you might change this. But the front cannot move too quickly. It depends on the support of the convolution. So this is sort of elementary Fourier analysis. Oops. So what's happening is you can do the following, which is very funny. You can pick your support function in such a way that you kill one of the frequencies. So you say, oh, I've got frequency 1,000. Then I can choose this function here exactly so that it averages the frequency 1,000, all frequencies 1,000, to 0. Which means I move the front, but I simplify the problem because my trigonometric polynomial now doesn't have 17 terms, it only has 16 terms. You induct, you're done. That's really, you can do this in an elementary Fourier analysis class. So this is it. And it works for spherical harmonics as well. It works for eigenfunctions of the Laplacian. It's kind of a very versatile argument. The problem I want to tell you is I think it's the wrong scaling. Like, look at this. I take this function and I take that function, and I'm saying, oh, you sum up the gaps, right? But that's not what's happening. The higher frequency one is not it's gonna cause trouble. I mean, maybe you can tune it in a clever way to move it out a little bit, but I find it very difficult to believe that it's really just summing all the frequencies. The 1D result that's sharp, in fact, does not address this issue because in the Tykov theorem, you start at a certain frequency and you go consecutively to the next frequency. So if you scale it like this, then yes, that's fine. That makes sense. But I think in general, it might be something like an L2-based quantity or something else. It shouldn't be the sum. Okay? Any questions? Okay, I've never made enemies by stopping a little bit early, especially on day 4. So thank you very much.